So I would like to talk about also some stuff, some work we've been doing, although I will not be going back to the 80s, although I could go back to the 80s, but I will go back only a few years. So you want a common theme of what we have been doing is the following. Lots of us and us, we started working on models of learning, focusing on issues of convergence or divergence to rational expectations. That's something there's a lot of. When I talk to my students about, there's a lot of work on convergence of models of learning to rational expectations, and that's kind of a well-accepted thing to do. That's kosher. You're not looked down on if you do that. But if you do models of learning and you try to test them, just see if the model of learning explains the data, or if you try to use the model of learning to draw policy implications, that's still a lot of the profession will look down on you. You're not supposed to do that. Models of learning have lots of degrees of freedom. You can get any result you want. But that's what we're doing. George did some of that, so we're not the only ones. There's more and more people doing this. I used to say to my students in George and Seppo's book, which was published 2001 or 2002. It's a 300-page book, and it summarizes a lot of the work done in the 90s on learning, and the amount of what the book devotes to empirical applications is like 2 pages or something like that. Okay, and that's a fair summary of what had been done. But since then, there's a lot more that has been done, trying to study empirical implications and policy implications of models of learning, and there's a lot more doing. The financial crisis has helped a lot. People in the profession are changing their view, and they are more and more interested in this. So one theme will be to look seriously at empirical issues and policy implications. The other thing we'll do is we'll emphasize in what sense our agents are not completely rational. So there's this issue that at some point, a lot of the work that George and that was presenting, that we had done, a lot of the work in adaptive learning, at some point, agents' behavior breaks up with rationality. Okay, at some point you have some expectation which would be rational and the rational expectations, but then you substitute it by something else. Okay, and there we have various words to justify that. We call it temporary equilibrium or something. But at some point there is an arbitrariness there, and we would like to deal with that. We would like to take out the arbitrariness and to. If you want, one way to think about it is we try to see if we can give micro foundations for the various approaches to adaptive learning that we have. And once we have the micro foundations, it's nice because then we can ask, well, is this a reasonable learning scheme or not? No? We have clear implications of the different assumptions. But we will be doing models of learning where agents don't have rational expectations. Although we will have agents that are rational. And I will be very precise in what sense I mean this. Okay, it's possible to make this distinction very precise. Okay, so I will talk about 3 papers. One is the one that George mentioned, Stock Market Volatility and Learning, with Klaus and Juanpa. Another is Internal Rationality and Asset Prices, where we discuss how to make it is more going at the micro foundations of models of learning. And then I will not discuss in detail because there will be no time, but I will talk about a paper on housing bubbles. So the first paper we wrote is this one on stock market volatility. We had a version 6 years ago or something like that, and it's still floating around journals. Where what we do is we look at in a specific way whether we can explain volatility of stock prices with a model of learning. So here we do formal econometric testing. Okay, the idea is we write down a model, we do econometric testing the way with the best testing procedure we can find for the model. And these are the facts. Well, somehow there is no picture here. There's usually, what happened to the pictures? There's usually a picture, but you've seen the picture. If you look at stock price over stock dividends, you see a lot of volatility. You see bubbles going up and down. And that's reflected in a very high volatility of the price-dividend ratio. If you look at quarterly data, the average price-dividend ratio is 113, and the standard deviation is 52. So it's like, if this would be normal, it would be negative very often. Okay, very high volatility. The serial correlation of the PD ratio is very high. Then the variance of the stock return is 12, the variance of the quarterly stock return. And if you would have, sorry, I don't have it here, but the variance of dividend growth, the variance of dividend growth is 1/4 of this. All right, it's about 3. So this is very hard to replicate with models of rational expectations. And we try to see if we can replicate all these facts. The other thing is the excess return predictability, whether you can predict 5 years ahead the excess returns with today's price-dividend ratio. And as is well known, if you do that simple regression, you get a negative parameter on the price-dividend ratio, and you get a significant, so you can predict long-run excess returns. That's another fact that we can see if the model matches. And then there's the equity premium with quarterly data is about 2% for this data set. Okay, so these are the 5 facts that we want to match. We take the excess volatility puzzle to be summarized in these 5, in these moments here. And this is a quick summary of what had been done. There's a lot of papers that have been written on stock price volatility and learning, and a very quick and unfair summary, but summary of what has been done is the following. Most of those papers, what they tend to do is they tend to say, well, let's say there is learning. So the stock price is given by agent's expectation. So the E tilde here represents agent's view about how to forecast tomorrow's stock price and dividend. And then most papers study Bayesian learning in the sense that then from here they write down this discounted sum, and they say, well, price has to be the discounted sum. We have been taught that this is the way prices are formed. And then if agents have in mind that, simplifying assumption, have in mind that dividends follow a unit root with some mean for the growth rate of dividends equal to A, and then if the Bayesian posterior of agents about the growth rate of dividends is A sub t, Then the fact that the agents have this discounted sum as the way they perceive prices are formed means that the pricing formula will be this one in a model of learning. So models of Timmerman, some of the models that George presented. There's a lot of, quite a few papers doing this. And the work of Bansal and Yaron can be seen as doing this in a certain way too. So basically there you can get volatility, but it's hard to get as much volatility as you see in the data, okay? It's hard to see this huge volatility we see in the data. So a quick summary is that Bayesian learning helps, but it's not enough. Now, what we do is a little bit different. Look at what these papers are doing. What they are doing is when they write this pricing formula, they are actually saying that the agents are learning about dividends, but agents know the pricing function. Agents know that there is a mapping from dividends, past dividends, to the price, and they know this mapping exactly. And it is only because they know this mapping that you can go from here. Whoops. It's only because of the, then we say, implicit assumptions, but it's only because you assume that agents know this pricing function that then you can say that this implies that. Okay? So this is kind of a very asymmetric. You start saying, well, agents have to learn, agents don't know, what do we know about how prices are formed? But then you assume that agents know how prices are formed, because you assume that agents know this function. In this world, they know how prices are formed exactly. They learn about dividends. So the first paper we wrote was kind of saying, well, why don't we say that agents don't know about prices? They try to learn about prices. We even give them perfect knowledge about dividends. We say, well, they know that how dividends are formed. They know the parameter A, if you want. You can introduce learning about parameter A, but what they really don't know is how prices are formed, and they try to learn about that. This is not the first paper where agents learn about prices. There's a list of others, but I think it's the first paper where agents learn about prices, and then we do econometric testing of the model. So this is what we do. We assume that agents have a model. In their mind, the agents have a model of prices and dividends. And this model implies a stochastic process for prices and dividends. And this script P up here is the perception, is the model that agents think to be true in driving prices and dividends. Okay, so the script P that will be in our expectations is denoting a stochastic process that agents are born with. Agents just think there is a certain model of how prices and dividends evolve. And then this is what determines prices. And then with this model, we're going to assume that they have a model where, well, there's really no assumption here. If beta t is the perceived growth rate of stock prices, then you go from here to here without any assumption. So if beta t is the perceived growth rate of prices, any system of beliefs P will give you this. Okay, it's just that the system of beliefs will give you a different beta. Different system of beliefs will give you a different beta. So we just, for now, say beta will be estimated from past observations by some Bayesian rule, and then we give them the true beliefs about the true process about dividends. So in that world, simple algebra tells you that, high school algebra tells you that this is the equilibrium. And then you can see it's clear that this is going to have bubbles that you're going to have a price going up, and then if something stops it, then the price will start going down, because you see there is inertia here. It's clear that if agents are optimistic, so if beta t is increasing, then this drives the price up. If it drives the price up, it drives the observed price growth up. So this will drive the beliefs up, and then the beliefs will drive the price further up. So this can create bubbles, and then you need to do something else to stop it. But once this is stopped, prices will go on. The reverse dynamics will also happen. So that the model has potential to generate bubbles is obvious. And what we find is that this generates a lot more volatility. It generates a lot of volatility. I mean, in a way, what happens is what's difficult in this model is to have not too much volatility. The excessive volatility puzzle becomes an insufficient volatility. Insufficient volatility puzzle, if you want. I'm not worried about that, because it's easy to put things in the model to make the price less volatile. So if we assume adaptive learning, so we assume that perceived price growth moves according to the adaptive learning formula, then this is the results we get. So the testing procedure is method of simulated moments. So here we just do econometrics, okay? This is a model with a hidden state variable. The beliefs of agents is a hidden state variable. We just use the price and dividend data. So beliefs is unobserved for us, and if you have an unobserved endogenous state variable, maximum likelihood is very complicated to do. What's the econometric procedure that's easiest to use is method of simulated moments. I won't go into that. It's just you pick parameters, you generate moments from the parameters, and you compare them to the data, and you try to make the simulated moments as close as possible to the true moments. And that procedure has an asymptotic distribution and asymptotic errors, and you can do all the testing you like to do with this procedure. So Christoph was there asking if there is a procedure. Well, this is a sense in which we can say without a doubt, with all the doubts of the standard procedure, but using standard procedures that we use all the time in economics, we can say, yes, we can match the data. A model of this type matches the data, because look, when we do formal testing, this is the list of the moments we try to match. There are 10 moments, I think, and 2 parameters. So with the 2 parameters, we could match 2 of the moments, but there are 8 degrees of freedom that we could fail to match, if the model would be false. So this is a list of the moments. I can answer questions about them. And this is the standard deviation of the moment. Okay, so you can compute the standard deviation of the sample moment. There's standard ways of doing that. Based on asymptotic distribution, this would be the standard deviation of the moment. So you can see, for example, maybe we don't match the mean of the PD ratio very well, but we shouldn't be worried about that, because this has such a big standard deviation. The moment has a big standard deviation. Okay? So this is the moments we try to match, and this is how much importance we should give to each of the moments. There was the question.
Yes, sir, but it's just an issue, which is you also have risk aversion here.
Yeah.
So you treat and you don't observe risk aversion.
Yeah.
So how do you go with risk aversion and observe and beliefs and observe?
There's another parameter. So risk aversion is could be another parameter that we estimate. What? Well, we have 10 moment conditions. So the results we'll show you are for fixed gammas. Okay, so I show you different results when we fix gamma to 2 levels. We could just estimate gamma and see what it is that we need. The problem is that not only in learning, in Hansen and Singleton, all the models, papers of stock pricing, when gamma is always very imprecisely estimated. In practice, you do GMM, you do anything. You change a little bit the data set, the estimation procedure, the algorithm, and gamma changes a lot. So we decided, instead of trying to estimate gamma, we show 2 points. But it's another parameter. And we have lots of degrees of freedom, so in principle, we could try to estimate. Yeah? So this table is for a very high risk aversion, okay, 80. It's 80, but this is what Campbell and Cochrane used, okay? There's at least 2 or maybe 3 rational expectation stories that can match, by now, stock price volatility. There's Campbell and Cochrane with a very strange model of habits, which has lots of problems that people have discussed. I won't go into it. There is Bansal and Yaron, which has perhaps less problems, but also, it's a rational expectation story that works. And there is, what's it called? Disasters, low probability disasters story, which also gives some of these moments. So to answer Christoph's question, there's also rational expectation stories that can match this data, We have to go a bit deeper to see which one is the best one. But in Campbell and Cochrane, you look at a footnote, the effective risk aversion that they have in their model is 80. Okay? If we do that, we do great. We match the Hansen and the over-identifying restriction, the test of over-identifying restrictions of Hansen or Sargan is accepted. These are the estimates of the constant gain and the discount factor. And these, perhaps more informative, these are the t-statistics of the moments, okay? This is the true moment, as I said. This is the estimated moment from the model at the parameter estimate. And if you take this minus this divided by that, and you have to adjust it to get the proper loss of degrees of freedom for technical reasons, then you get these t-statistics. They are incredible. I mean, it's just, we take here the most basic, model of asset pricing is just no habits, nothing, just constant relative risk aversion utility function. The most basic model of dividends, just unit root for dividends, which they are not. They are, the growth rate of dividends, in fact, is serially correlated, as in the Leibson paper that George was mentioning. We take constant learning. We didn't do any fancy, any strange thing to beliefs either. Okay, all we add is learning about prices, and this puzzle, which took like 30 years to solve before Campbell and Cochrane came up with a model that actually explained the volatility. 20-something years from Grossman and Schiller to Campbell and Cochrane to get a model of rational expectations that match the volatility. This is done with the simplest possible model. If we go to lower risk aversion, gamma equals 5. Okay, so we fix gamma because in that way we can compare where we fail and where we don't fail. We do pretty well, but we fail the test of over-identifying restrictions. This test would reject the whole of the test. And this would be because we don't match the risk premium. Basically, I don't have time to go in detail into this, but basically with gamma equals 5, we cannot explain exactly the risk premium. We have a risk premium. There is a risk premium in the model, but we don't get quite there. The estimated risk premium is 1% per quarter instead of 2% per quarter as in the data. Okay, so we don't quite get there, but we get some of the way. We're not too worried about that. This model didn't have much. There's lots of other things we could add if we wanted to match the risk premium. But anyway, for a reasonable risk aversion, we don't get there for the risk premium. That's the summary of that paper. So how am I doing on time? So I have what? 15 minutes?
30.
What? 30 more minutes. Okay. So when we were presenting this paper, we were getting the criticism again and again that if agents did this, if agents go from this equation to this equation, agents are very stupid. Okay, the way a famous economist put it in one of the talks was, your agents can't add 2 plus 2. We were making this claim as that our agents are very rational. Our agents are very rational because they are maximizing the utility, and also because the model they have in mind is very close to rational expectations. Okay, so we have a story that our agents are very rational. But the criticism we kept finding was, if agents go from here to there, and the agents try to forecast prices independently from dividends, our agents are extremely irrational, because agents should realize, because they are, rationality means that agents know that prices have to be equal to discounted dividends. Okay? This is the criticism we kept finding again and again. I guess Stephen there's an Allen, Morris, and Shin story about why that shouldn't be the case, but then they would say, in our model, this has to be the case. Okay? And then we didn't think this was true. So we wrote this separate paper on rational learning about prices, about how, there's a story where agents are perfectly rational, but just because they don't know exactly the truth, there's no reason why they why they have to have prices equal to discounted dividends. So this other paper is kind of trying to justify that, but also in the process, what we find is that perhaps this idea that I'm going to talk about is a way of giving micro foundations to lots of the models of adaptive learning that people have been using. Okay, there's lots of models of adaptive learning. That's like George was presenting models where expectations are like this, expectations are like that, expectations are like this, and then they're like that. No, there's lots of options. Not too worried about that. One could say, people who do rational expectations, they also look at utility functions that are like this, utility functions that are like that, or production functions or frictions. People who do rational expectations also give themselves a lot of degrees of freedom when modeling utilities or other parts of the model. It shouldn't be such a big sin that we model expectations in different ways. Okay, so that's per se not a bad thing, I think. But I think it's good to have we think it's good to have a unifying framework where which allows you to think all these options, how do they fit together into one concept, okay? And perhaps this is a way of thinking about that. So in this paper, we consider agents who are completely rational. They are rational in the sense that they maximize utility. These are agents who have taken a first-year PhD course, so they know how to do dynamic programming, filtering. They know how to do Euler equations and solve them numerically. Okay, they know exactly, perfectly well to maximize dynamic maximization problems. So in that sense, we say they are internally rational. They know how to do the best for them and their families. But these agents don't have rational expectations. They just don't. Okay? They have a belief about how prices evolve. They have a belief, actually, about how all the exogenous variables, all the variables that are exogenous to them evolve. And they maximize utility given those beliefs. Okay? So those beliefs will be usually specified in terms of a model which may have drifting parameters or unknown parameters. But we're going to say agents have these beliefs. And these beliefs are going to imply a stochastic process for prices and dividends, and if there would be taxes, anything that is exogenous to their choice. They have a belief about that. And given the system of beliefs, they maximize the utility, and the restriction implicitly, but sometimes explicitly, we put on the beliefs of the agents is that the model that generates these beliefs has to be reasonable. Okay? It has to be a model which is not obviously, blatantly rejected by the data. No? If we have agents with a model, agents have a model in mind, then we can ask the question, is this a model that the data would sustain? Is this a model that the model would sustain? Is this a model that would be obviously rejected? This goes back to, if you want, this paper kind of puts together ideas that have been around. There's an old paper in the 80s from Bray and Sabin, which already did this, okay? Already talked about how if agents learn, what they see could be completely rejecting the model, okay? So but by insisting on internal rationality and then specifying separately the beliefs of the agents, then we can ask specifically this question at every step of the way. The only thing you have to be careful about is now how you define the state space. Okay, so what you should be doing is the following. You now assume that agents see prices as an exogenous stochastic variable, right? So as such, it would be reasonable that agents, competitive agents, take that as given. So in their state space, the amount of shocks they receive, there would be the whole history of prices. So if you let omega p be the future histories of prices, and omega d be future histories of dividends, and omega the Cartesian product, so omega is now joint histories of prices and dividends, then, well, this omega is their state space, is what they see as the things that could be happening to them. And then it will be optimal, it's not just an assumption, it's just optimal, that if they see these things as exogenous, agents would be conditioning their choice of consumption. S would be the stock price, the stock holdings, anything they choose would be a history of past shocks, including past prices. Okay, so here I use the notation, the superscript is the history up to dt. Okay, these agents see themselves as making choices of consumption conditional on what they've seen about dividends and prices. Now, this is reasonable. This is optimal behavior. It's also reasonable with competitive agents that they would see prices as shocks. But this is not what we do. This is not what we teach students to do, right? Is there a student here? If there's a student, don't do this in the next exam because they'll take some points off. In the next exam, what you should use is this. No, this is what all the models are. Often even only implicitly, we don't even write this anymore because it's implicit that we see our agents as choosing, making choices contingent on histories of the fundamental shock, in the case, in the stock price model. I'm looking at would be histories of dividend. Okay, this is what we do. And this is okay. This is the same as that, okay? This is the same as that in the case when agents know the pricing function, which is what we assume when we make the rational expectations assumption, but also is what we assume, Timmerman and all the others assumed, okay? Bayesian rational learning also assumes that agents know the pricing function. So, of course, if agents know the pricing function, putting prices in here is a waste of ink. Well, I guess I should say it's a waste of black pixels because there's no additional information, no? So this is okay, the standard practice is okay if you impose this singularity, but we say, well, there's no reason to impose this singularity. Why would we talk about learning if then we're going to give agents this superior knowledge that not even economists have, no? George was talking about cognitive principle. Us as economists don't know P of D, do we? I mean, we write one paper with one P and then we write another paper with another P, so it must be at least somewhere in the middle. So we say agents don't know this, agents don't, what agents have is a belief about, agents have a probability measure, script P, on omega, on on stochastic processes of prices and dividends. And that's what they do. They maximize given that. And this is reasonable since economists don't know the mapping. And then, well, given this belief, script P, the agents maximize their utility function. There's no sin at all. If you don't think it's a sin saying that agents don't know the pricing function, there is no sin. There's nothing to be ashamed of as an economist of anything in the paper. Agents maximize this standard utility. You could give this problem to an engineer, and he would give you the same answer. Okay? Agents are maximizing. The first order condition of this problem with a risk-neutral agent, U, risk-neutral utility, is this one. The first order condition is not discounted prices. Okay? And perhaps I didn't write this properly. I should have written this with an inequality, no? Because you see, agents, we write this as an equality because we know that in equilibrium there's an interior solution, etc. But agents don't know that. Agents think that they might be against the short selling or a leverage constraint. So maybe agents think that there's a possibility they will be credit constrained. So this, for the agents, actually holds as an inequality. So they, given their beliefs, would be crazy to infer this. Would be wrong. Okay? The discounted sum only holds for us as economists, because we know in this economy with homogeneous agents, they won't be trading, and so they won't be against the constraint. But agents don't know that. Therefore, you can't go from here to there. So in that sense, there's an alternative to Alan Morzanchine and other ways of coming up with prices. Rationality doesn't mean that prices are equal to the fundamental, to the discounted sum of fundamental, whatever is the fundamental for the asset. You could go from here to there if, in addition, agents are assumed to know the pricing function, and or if there is, or they know that there is no bubble solution, and they know, in a model with, here I don't have heterogeneity, but in a model with heterogeneous agents, there is agents with different beliefs. There's only one of them. The most optimistic one is the one that's buying the asset, right? And it's the most optimistic one is the one that's pricing the asset. You would have to know everybody's opinion in order to go to a discounted sum. You would have to know who is pricing the asset each point in the future. So discounted sums are not don't imply rationality. So the belief specification that's compatible with adaptive learning in this model then is this one. Assume that agents have in mind a model where the growth rate of prices follows a process beta ht, and beta ht is itself a unit root, and it has an initial condition. Okay? If you just say that agents have this model in mind, you can then make this as close as possible to rational expectations as you want. If you assume that the initial beta hat, the forecast of beta ht, is very close to the rational expectations value, which is A, the growth rate of dividends, and you make this variance extremely small, this is rational expectations, because in this, well, with sigma 2 beta equals 0, agent's perception, you would have the rational expectations equilibrium, okay? So this nests rational expectations. So we try to look for models where there is adaptive learning, but where sigma square beta is very low. And therefore, in that sense, you're close to rational expectations. So there is a specific, you have agents, what agents would believe under rational expectations, what agents believe here, and the distance between the two probability measures is very small. Okay, this is, in that sense, this is a small deviation of rational expectations. We can also ask, is this a model that the data would be rejecting? Obviously. And the answer is, well, it would be hard for the data to reject this. There's a sense in which it would, but no, it would be hard. And there's this other paper on housing booms. We basically argue that housing bubbles can be explained by rational learning. But perhaps to this audience, it is more, I think, more interesting to emphasize that with this idea of internal rationality, I find it useful because then there is lots of issues that, to my mind at least, become much clearer. For example, there's been, if we have these different types of models, as we saw in previous talk, we could ask, what do agents have to believe about the world so that this or that learning model are the optimal behavior? Okay, if we did that exercise, perhaps not everything goes through, right? Perhaps we can see clearly that some of these models that agents would need to have in order to justify this belief are just, unlikely to be true. After all, we do have data on expectations, right? We have surveys, we have experimental data, we know a little bit how agents behave and what is the model they have in mind. So this can help with that. There's also been two types of modeling how agents' forecasts are incorporated into a decision making. This has been around since the 80s again, but lately George and Seppo were using in many of their models one step ahead forecasts. So you take it's like like what I did, okay? You take the Euler equation one step ahead, you look at the forecast of the model for that expectation, and then you look at the dynamics from there. And then Bruce Preston is advocating something different. He says, well, let's go to the budget constraint of the agent. And in there, I plug in my perception of the future. And that gives a different, it's two different alternatives. Who is right, one or the other? They are both wrong, and they are both right in principle. But what happens, as we could see, what happens here is that there are these two cases where the one step ahead forecast is optimal. It's just optimal behavior. One is risk neutrality. And the risk neutrality, the one step forecast, is optimal behavior. And also, if agents are risk averse, but as the amount of dividend relative to aggregate income goes to zero, so if the amount that stocks paid is very, very small, also in that case, one step ahead forecast is optimal. Okay? But if you go to risk averse, a model with risk aversion, where the stock is a non-negligible, is a large part of aggregate income, okay, risk aversion and the stock really matters for your stochastic discount factor. We're doing that in a separate paper with Klaus, which you can find around the web. If you do that, then one step ahead forecast is not optimal. Then, the agent is taking into account that the uncertainty about prices matters for his stochastic discount factor, and then we haven't done the comparison, but then the kind of learning that Bruce Preston does is probably, it's still an approximation, but it's probably a closer approximation, because then there are wealth effects that the one-step forecasting rule kind of misses. So, what is the optimal rule? Well, it depends on your utility function and the endowment. We can give an answer from micro foundations. We also can ask the question, is it right or is it wrong to have agents with different beliefs? Well, we know how to get that, right? Different priors, even if agents have the same model, okay, but different priors, which can come from different experiences, from different education, well, we don't care. Different priors can give you different beliefs. And one can look at whether there is priors that will give rise to the heterogeneity you need to get a different, certain behavior in your model with heterogeneous beliefs. Another issue that has come up, the projection facility. Projection facility means that agents, at some point, they discard observations, okay? If you do that in a gradual way, if you say that agents, if the last observation would mean a very large estimated growth rate, then they don't ignore it, but they discount that observation. They discount observations that would send their beliefs away. This is consistent with agents who have a prior on parameters which is truncated. Because if it's truncated, if prior on parameters is truncated, you downplay observations that get closer and closer to the upper bound. Okay. Anyway, there's lots of issues that, at least having an internal rationality framework in mind, we have a common, we can clarify where the differences can come from. But also, perhaps more important, with this I will finish actually, we can then ask, is this a reasonable model that agents could have? Okay, so I wrote this. Is this a reasonable model that agents could have? Agents basically see stock prices as having a growth rate that drifts. They're not sure if it's high or low. They try to constantly learn about it. Is this We can ask people. We can look at data if it blatantly contradicts this. You know, it gives a clear framework for testing beliefs. So that's.
Okay, thank you very much.